Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 13 of condensed matter physics, in which I'm going to discuss Fermi surfaces today, and I'll solve questions related to that. So also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and also share my lecture details to your friends, so that they can also be able to watch my free live lectures and they can also be benefited by it. Okay, so let's get started. Fermi surface. Let me meanwhile let me check. Just let me check whether I'm audible or not. Fermi surface. Meanwhile let me. Okay, yeah, I'm audible. So I'll proceed further. Okay, guys. So Fermi surface. Fermi surface. Okay, Fermi surface. So Fermi surface. So first we know that energy, Fermi energy is EF. We can write EF h cut square upon 2m, h cut square upon 2m into kf square, right? This is the Fermi energy, right? So Fermi surface in 1D is a line, guys, just a line, okay? And in 2D, the Fermi surface is circle, okay? Circle. And in 3D, the Fermi surface is sphere, guys, okay? Sphere. This is simple, basic information, okay? And if we talk about a direct lattice, okay, in direct lattice, the square is that. So Fermi surfaces in 2D we are going to say, right? Fermi surfaces, Fermi surface, Fermi surfaces in 2D. In 2D. So we are going to study Fermi surfaces in 2D. Okay. So if you talk about direct lattice, if you have a square, right? So this is the A and A. Okay. So this is direct lattice, guys. In direct lattice, square is represented like that. Okay. So if you talk about that reciprocal lattice, right? So there is a this one. Okay, so this is 0 minus pi by a, right? This is pi by a comma 0. This is 0 comma pi by a, and this is 0 comma minus pi by a. Okay, and this is kx. Okay. So this is reciprocal lattice, right? Which is represented in momentum space, right? Reciprocal lattice. I have explained it already in my previous lectures. Reciprocal lattice. Okay, and this is this is the first Bravais zone, right? Okay, first Bravais zone, that is first Bravais zone. Okay, first Bravais zone. This we know, right? Is reciprocal lattice is represented in momentum space, and this is the first boundary of Bravais zone. Okay, so this is the first Bravais zone in the reciprocal lattice. Okay, so now we'll study the case 1. Okay, and this we know, guys, this total distance is 2 pi by a. Okay, okay, so now there are two cases which we are going to study. Case 1, Case 1 is for monovalent atom, monovalent metal. Okay, monovalent metal. So if we talk about monovalent metal, means there is one in the card. So that is one electron, right? Monovalent metal like sodium. Okay. This is monovalent metal. Okay, requirement of one electron in the monovalent metal. So for that you need to understand the area. So now this is the first Bhreva zone, right? We know. So area of first Bhreva zone we know. That area of first Bhreva zone. Area of first Bhreva zone I'll write in short. Okay, first Bhreva zone, BZ I'm going to write. So area of first Bhreva zone, that is, we know that is 2 pi upon a whole square or 4 pi square upon a square. I have already explained the area of first Bhreva zone, second Bhreva zone and third Bhreva zone. Okay. Okay. So now area of Fermi surface. Okay. Area of Fermi. So in 2D I have explained area of Fermi surface is circle. In 3D it is sphere, right? So area of Fermi circle, Fermi surface, area of Fermi surface, that circle, right? Area of Fermi circle. So area of Fermi circle is area of Bhreva zone, because Bhreva zone, okay, by 2. Okay, so area of first Bhreva zone, second Bhreva zone, third Bhreva zone is same. Okay, that is 4 pi a square 4 pi square upon a square. So area of Fermi surface is area of Bhreva zone upon 2. Okay, area of Bhreva zone upon 2. Well, now so Fermi surface we can write pi kf square. Okay, here you need to understand, because there's a Fermi surface in reciprocal lattice, right, in momentum space. So kf is radius of the circle. Okay, where kf equal to radius of circle. Okay, so this is the area of Fermi surface is going to be equal to area of Bhreva zone. We know that is 4 pi square upon 2a square, right? So from here we can get value of kf. Pi will get cancelled. Value of kf is going to be this one, root 2 pi upon a. Okay, and we can also write it root 2 upon pi into pi by a. We can multiply by pi and divide by pi, right? So this is going to be this, and this value, if you get this value, is going to be 0.79 pi by a. 0.79 pi by a. This distance is pi by a, right, in first Bhreva zone. Okay, this is important. So this is the kf. Okay, Fermi surface. So this is 0.79 pi by a. Okay, so this means, this implies this this radius of Fermi surface kf is between 0 to pi by a, right? Because this value is 0.79 pi by a. So area of the Fermi surface is between 0 to pi by a, because it's 0.79 pi by a. Okay, important thing. Now, so in this case, what will happen? That implies Fermi surface will completely lie inside the first Brillouin zone, right? Because we can see this area of circle is this 0.7, that radius of circle is 0.79 pi by a, right? So that will be inside this uh, first Brillouin zone, right? So we can write, okay, meanwhile let me just check whether I'm audible or not. I think I'm audible, I have already checked. Okay, so Fermi surface, so Fermi surface will completely lie inside the first Brillouin zone. Okay, BZ I'm writing in short, first Brillouin zone. Okay, this one, it will completely lie within this zone, first Brillouin zone. Okay, okay, so like I can make figure like this. This is, okay, so this is a pi by a comma 0, this is minus pi by a comma 0, this is 0 comma pi by a, and this is 0 comma minus pi by a. Okay, and so this is the circle, that Fermi surface will be completely inside this, because the radius of Fermi circle is 0.79 pi by a, right? This is the one. Next is second case we are going to study. I hope you have understood it, guys. Second case, case second is, and so case second we are going to study. Case second is for divalent metal. Okay, for divalent metal, for divalent metal, that is 2 electron, right? Efficiency of 2 electron for divalent metal I'm talking about. Okay, for divalent metal, this this is important. Okay, for monovalent we have seen area of Fermi surface is area of Brillouin zone by 2, right? So case second is for divalent metal. Okay, area of Fermi surface is going to be equal to area of Brillouin zone. Okay, area of BZ. Okay, area of Brillouin zone. So for this is going to be pi kf square, that is circle, right, into the, and this is the case for divalent metal I'm talking about. So area of Brillouin zone is going to be, that we know, 4 pi square upon a square, or 2 pi by a whole square, right? So from here the value of kf is going to be, you can easily solve it. So value of kf is going to be 2 upon root pi by a. Okay, so for kf is going to be, this value is going to be almost equal to 1.2, okay, 1.182, 1 point 1.182, 1.1, sorry, 1.128 pi by a. Okay, so this is the radius of Fermi circle, or radius of Fermi surface, that is a circle in, that is circular. Okay, in case of divalent metal. Okay, This is the divalent metal. Okay, so if we make a figure for this, so this is going to be like this. In first Prima zone, this is first Prima zone, guys, very important. This is Kx and this is Ky, right? This is the first Prima zone. This is first Prima zone. First Prima zone, okay. So this one is going to be circle like this. Okay, consider this is circle. Okay, so here, because why, if we talk about, this is the pi by a, right? This pi by a comma 0, this distance, but this distance is root 2 pi by a, right? That is 1.4 1.414, right? 1.414 pi by a. So this is greater than this value, right? 1.128. So in this case, for divalent, in case of divalent metal, Fermi surface does not include the corners of the first Brima zone. Okay, so Fermi surface does not include corners of first Brima zone. Okay, okay, so this one, because this value 1.414 is greater than 1.128, right? So in case of divalent metal, the Fermi surface does not include the corners of the first Brima zone. Okay, this is the one. Okay. Next is, so here I'll tell you very important things, then we'll solve question. Okay, so these are the Brima zone. Okay, so if we've got this circle like this is circle, guys. Okay, if it is not looking circle, consider it circle. If it is the case, then it means the Fermi circle, that Kf is equal to pi by a, right? The radius will be equal to pi by a. So I'm talking about first Brima zone. Okay, so in this case, just touches Fermi surface, means Fermi circle just touches, this is a 2D case. Okay, just touches the first Brima zone, right? If this is the case. Second case would be like this. This is the circle. Okay, going to be like this. This is going to be like this. Okay, this is the circle, guys. Okay, so in this case, you can see this is the first Brima zone, and this is the circle which is touching the corners of the first Brima zone. Okay, so in this case, what is going to be happen? Kf is going to be equal to root 2 pi by a. Kf is going to be equal to root 2 pi by a, right? Because that will be equal to this, because we can see this is the first Brima zone. Okay, this distance is pi by a, right? And this distance is root 2 pi by a. Okay, so Kf, that radius is going to be root 2 pi by a. Okay, and that means includes corner. That Fermi surface includes corner. Includes corner. Includes corner. Okay. And the third case we can see like this. This is the Fermi circle, and this is the first Bhrima zone. Okay. So in this case, what happened? Completely encloses the first Bhrima zone, right? Completely encloses the first Bhrima zone BZ. Okay. So KF is, in this case, KF is greater than root 2 pi by, right? Because in the KF is equal to root 2 pi by a if this is the case. In this case, KF is going to be greater than root 2 pi by a. Okay. Fourth condition is here. This is the first Bhrima zone. Okay. And this is this one, right? So this is, in this case, you can see Fermi circle is completely encloses by first Bhrima zone, right? So completely inside the first Bhrima zone, completely inside the first Bhrima zone. Okay, this is the case. So these are the different cases. Okay, and one more case is remaining. That's I'm going to tell this one. Then we'll solve one question. This one we have already studied, right? This one does not include the corner. So this is the one. This is circle, guys. Okay, consider it circle. So this circle doesn't include the corners. Okay, so in this case, root 2 pi by a is greater than kf is greater than pi by a. So kf is between root 2 pi by a and pi by a. So now in this case, so kf is greater than less than root 2 pi by a and greater than this one, pi by a. Okay, so does not include the corner. Yeah, that is does not include the doesn't include the corner. Okay, guys, so this is the important thing. Okay, so these are different cases of Fermi circle, when it encloses, when it is not enclosing the first Bhrima zone. Okay, now on the basis of this, I'm going to solve one question. Okay, very important question which is asked in CSIR net 2022. Okay, so question, I'm going to solve it. Very good question, guys. So I'm going to solve it. I'll write the question first. Question. asked in CSIR net. Okay. CSIR net. So question is, a certain 2D solid, a certain 2D solid, a certain 2D solid crystallizes crystallizes crystalli- crystallizes to a square to a square. So we have a 2D solid that crystallizes to a square monoatomic lattice. Okay, monoatomic monoatomic lattice monoatomic lattice with lattice constant A, with lattice constant A, with lattice constant A. Each atom can contribute each atom can contribute each atom can contribute an integer number of an integer integer number of free conducting electrons. The minimum number of electrons, the minimum, I have solved this question in my in 2020 paper, guys. You can check that. So the minimum number of electrons each atom must contribute such that the free electron Fermi circle at zero temperature so Fermi circle at zero temperature means it is talking about Fermi surface, right? Zero temperature, at zero temperature encloses the first Brillouin zone. Okay, first is that I'm writing in short, Brillouin zone completely. Okay, options are, option A is 3, option B is 1, option C is 4, and option D is 2. Okay, so this is the question, guys. Well, I'll read the question. Question is, a certain 2D solid, so we have a 2D solid, okay, that crystallizes to a square monoatomic lattice. Okay, so that gets crystallized to a square monolattice, okay, with lattice constant A. Each atom can contribute to an integer number of free conducting electrons. Okay, so the minimum number of electrons each atom must contribute, okay, such that the free Fermi circle at zero temperature encloses the first Brillouin zone. So that's what we need to find out. So minimum number of electrons that each atom must contribute such that the free electron Fermi circle, that is Fermi surface, 2D Fermi surface at 0 temperature, encloses the first Brimah zone. That's we need to find out. So minimum number of electrons we need to find, right? So very simple question. So now we know in 2D, in 2 dimension, we know Kf, that is Fermi wave vector, that is the radius of Fermi circle. Kf we know that is in 2D 2 pi n upon a to the power 1 by 2. This I have already explained in my previous lecture. Please check it. Okay. So this is the one. Now since this is the Kf, right? And since we know, because it is asking for the minimum number of electrons that must contribute such that the free electron Fermi circle at 0 temperature encloses the Fermi first Brimah zone completely, right? So in this case, what is going to be happen? That Kf must be greater equal to root 2 pi by a. This you need to understand. Kf must be greater equal to root 2 pi by a, because we know if Kf is equal to root 2 pi by a, it just encloses the first Brimah zone completely. Okay, it encloses the corners of the first Brimah zone as well, just complete it, right? So that should, so it means Kf should be either equal to this or greater than this. Okay, this is important. I have explained here. You can see we talk about this, right? So if Kf equal to root 2 pi by a, that includes corner, it just encloses the first Brimah zone. Okay, it just encloses the first Brimah zone. In that case, Kf is equal to root 2 pi by a. So here we need to find minimum number of electron. Okay, and that must contribute such that the free electron Fermi circle, that is Fermi surface, encloses the that completely, right? So this means this should be equal to, this should be greater equal to root 2 pi by a, right? Now we'll put the value. Okay, so Kf value we know that is 2 pi n upon a to the power half, or we can write root, right? Root, and this is going to be root 2 pi by a. Root 2 will get cancelled, and here we know a, area of this Fermi surface, right? The a area, that is area of lattice, right? That is we know a square, right? Because this is the lattice, right? This is square lattice. Mono it 2D solid crystallizes to square monoatomic lattice, right? So this means this is a square, right? So this is going to be root 2 pi n. N is the number of electron. Okay, root 2 pi. Okay, root 2 got cancelled. So this is root pi n upon a square equal to pi by a. So a will also get cancelled. This a square means a, right? This will get cancelled, and pi will also get cancelled by root pi, right? This one, this is the one, right? Or we can write this, pi will get cancelled by this, right? So this value is going to be root n upon pi greater equal to 1. This is greater equal to 1, greater equal to 1. Okay, so from here we'll remove the root. So this is n upon pi greater equal to 1. That implies n is greater equal to 5, and this value is 3.14. Okay, so it means n should be either 3.14 or greater than that, right? So which option is matching, guys? Option C, 4 is matching. Okay, this is either it is 3.4 or it should be greater than this. Okay, so this condition is very important, guys. Okay, okay, for closing, so this is for closing this one, that the contributes such that the free electron Fermi circle at this concludes the first Brimah zone. So for closing first Brimah zone, Kf must be greater equal to root 2 pi by a. Okay, I hope, guys, you have understood it. Next question we are going to solve. Next question is, Next question is, this is also good question. Consider a 2D square lattice, a 2D square lattice, 2D square lattice. Okay, consider 2D square lattice. The ratio of the ratio the ratio of the ratio of the kinetic energy of the kinetic energy ratio of the kinetic energy ratio of the kinetic energy of free electron of a free electron of a free electron ratio of kinetic energy of a free electron, okay, at the corner at the corner at the corner of the at the corner of the first Brima zone, corner of the first Brima zone, that is EC, that is kinetic energy, okay, EC, to that of an to that of an to that of an electron to that of an electron at the midpoint at the midpoint at the midpoint of the side of the side face of the same zone, side face of the same zone, EM is, okay, that is EC upon EM. Okay, we need to find EC upon EM is option A is 1 by 2, option B is 2, option C is root 2, and option D is 1. Okay, so this is the question, guys. Very simple question. This is given consider a 2D square, so we need to consider 2D square lattice. Okay, the ratio of kinetic energy of a free electron at the corner of first Brima zone. Okay, that kinetic energy at the corner of first Brima zone to that of an electron at the midpoint, which is at midpoint of the side face of the same zone, EM is. Okay, I'll explain it. Very simple. I'll make a figure first. So this is first Brima zone I'm going to make. This one, okay. So this is kx and this is ky, right? And this is pi by a comma 0, first Brima zone is, okay, minus pi by a comma 0, and this is 0 comma pi by a, and this is 0 comma minus pi by a. Okay, so this is the first Brima zone. So what we need to find out, the energy at the electron at this corner of the first Brima zone at this point, and the second electron is an electron at the midpoint of the side face of the same zone at this point. The kinetic energy at this point and kinetic energy at this point. At this point energy is EC corner, and at this point is EM. We have to find the ratio of that. This is what it is asked in the question. Okay, very simple. This is the first Brima zone at the kinetic energy at the corner, kinetic energy of electron at the corner of the first Brima zone to that of side face, to that of an electron at the midpoint of the side face of the same zone. Okay, this midpoint of side face, this is side face of the same zone. Okay, so this is what we need to find out. Very simple, guys. We know here EF, Fermi energy, right? We know, very simple. EF is, we know, that is h cut square upon 2m, h cut square upon 2m kf square, right? This is the EF, h cut square upon 2m into kf square, right? So here it is a 2D case, right? In 2D we know, in 2D vector k that is equal to, or we can write directly this one, kf square is kx square plus ky square, right? And in this is in 2D, and in 3D, kf square is going to be kx square plus ky square plus kz square. Okay, so this is in 2D and 3D. Okay, so now we are going to find EC, kinetic energy, EC at EC upon EM, right? Kinetic energy at corner and kinetic energy at midpoint of the side is of the same zone, right? So we'll just put the value. EC value is this one, h cut square upon 2m. This is the same, okay, and this is kf square is going to be kx square plus ky square, okay, and upon here, because why this is kx square ky square, right? And here it is going to be h cut square upon 2m this is k dash x square, because these are different, right? K dash x square plus k dash y square, okay. So this will get cancelled, and kx square plus ky square value, this we know, right? This one, these are the corner atom, right? Pi by a, at this point the point are pi by a comma pi by a, right? Kx square plus ky square is this one, pi by a square. So EC upon EM is going to be pi by a whole square plus pi by a whole square upon this kx square plus ky dash square, right? This one, at this point points are coordinates are pi by a and 0, so this is pi by a square plus 0 square, right? So this is going to be simple 2 pi by this value is going to be 2 pi square upon a square, 2 pi square on a square upon pi square upon a square, right? This value is going to be 2. So this value is going to be 2. So 2 is the answer. Which option is matching, guys? Option B. Okay. And if it is in the, if we talk about 3D, okay, if question is asked in 3D, it is the case of 2D, okay. In case of 3D, for 3D, or in case of 3D, EC upon EM is going to be, so their coordinates will be at this point, this will be 3 pi by a, pi by a, pi by a, here pi by a and 0, right? Pi by a, 0 and pi by a, right? So this is going to be simple pi by a whole square plus pi by a whole square plus pi by a whole square, right? Upon pi by a whole square plus 0 plus pi by a whole square, right? And this value is going to be 3. Okay. Well guys, so I'm going to okay guys, so before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, well, and also guys, I would request you, please share this my lectures with your friends as well, so that they can also be able to watch my, they will also be able to watch my free live lectures. Okay, okay guys, thank you so much, bye now.